Welcome back from break. We are going to continue to be talking about solubility rules. And now we're going to do another question in which we can utilize the solubility rules in order to answer the question. So part C of the in-class worksheet is an exercise in which you will be determining what will be the correct solvent that you need in order to make a solution for a particular compound that is given. Okay, so as you can see here, we're going to have two different types of solvents, either a polar solvent, which is going to be, for example, water, or a non-polar solvent like hexane. The goal of this is to determine what's going to be the correct solvent to make a solution. So whenever we do this problem, the first thing that we need to determine is going to be if we're dealing with an ionic compound versus covalent. Because once you determine that, the approach to answer the question is going to depend on that classification. If you're dealing with an ionic compound, then we have to apply solubility rules for ionic compound. If we're dealing with a covalent compound, we need to draw the Lewis structure, determine the polarity of the molecule, and then select the correct solvent to make our solution. So taking that into consideration, let's determine I'm going to do 1 through 8 with you guys, and then I'm going to give you a few moments so you guys do 9 through 15. So the first question I'm going to ask you, and then please put in the chat. Put in the chat the numbers for the ionic compounds in numbers 1 through 8. Which numbers correspond to ionic compounds in numbers 1 through 8? I don't see any numbers in the chat. From numbers 1 through 8, which ones are ionic compounds? This is a review for the exam. Come on, there's 22 of you out there. We cannot forget how, if we look at something, we determine if it's ionic or covalent. Number 2 is not an ionic compound. Number 7 it is. Let me give you a hint. There's 2 more, and it's not number 2. It's not number 1. Number 8, we're missing 1, you guys. Excellent. Number 4. Don't be shy, you guys. We're halfway through the semester. We cannot run out of gas right now. We still have 3 more weeks to go. I know that this, I warn you, in the beginning of the semester, this course accumulates a lot of information. Let's just keep on being strong, being present, and knowing. And if you don't know, please ask questions. So that means that when it comes to the covalent compound, number 1 is a covalent compound, number 2, number 3, number 5, number 6, those are covalent compounds, okay? So again, when it comes to 4, 7, and 8, as you can see, some are given in words, some are given the chemical formula. We can utilize solubility rules to determine if they are soluble in water or not. So what that means is that if soluble in water, then a polar solvent can be used for forming a solution if insoluble in water a nonpolar solvent can be used to make a solution. Okay, that's how we determine that. So let's go to our solubility rules. Okay, so here we have strontium sulfide. Let's put in the chat, what is the chemical formula for strontium sulfide? Excellent. SRS. What about barium chloride? What is the chemical formula for it? Barium chloride. Excellent. BaCl2. Here, I put fluoride. Let me change it to another ion that you guys have in the table, because it will be making it easier. Instead of fluoride, let me do bromide. Okay, so we have those three. So when we go to the rules here, we have SRS, we have BaCl2, and we have FeBr3. So for this, we're going to determine if it's soluble in water or not. So this is a yes or no answer. Strontium sulfide, based on the rules, is it soluble in water? Yes or no? You can put a Y or you can put an N on the chat. So strontium sulfide is not soluble in water. Remember, sulfides, based on rule 5, are insoluble in water. And here we have it paired with strontium. The only thing that makes a sulfide be soluble will be lithium, sodium, potassium, or ammonium. Okay. What about barium chloride? Is that soluble in water? Yes or no? Excellent. Yes, it's soluble in water. What about iron 3 bromide? Is that soluble in water? Yes or no? Y or N? Great. I see that people are understanding solubility rules. So iron 3 bromide is also soluble in water. So when it comes to this question, okay, since strontium sulfide is not soluble in water, in order to make a solution, it needs a non-polar solvent. So I'm just putting NP for non-polar, putting P for polar just because of space. Barium chloride and iron 3 bromide, because they are soluble in water, if I want to make a solution, then I need a polar solvent. Okay, remember that the goal here is what solvent do I need to make a solution? Okay. For number 1, number 2, 3, 5, and 6, because they are covalent compounds, I need to do the Lewis structure for them. For covalent compounds, draw Lewis structure. Determine overall polarity of molecule. Select a solvent that matches the polarity of the molecule. So I'm going to take a moment and I'm going to draw the Lewis structures for these molecules, okay? Okay, so let's go back to the rules for overall polarity. Let me just zoom in into my structures, okay? So I'm going to guide you guys through determining the overall polarity of this. So CHCl3 is a tetrahedral molecule that does not have 4 identical bonds to the central atom. So again, putting P for polar, NP for non-polar. What is the polarity of this molecule? Excellent. Number 2, we already did it in the last, in chapter 6. H2S, tetrahedral molecule, again, that does not have 4 identical groups. Is it polar or non-polar? Excellent. So this is a polar molecule. Number 3, that is acetylene. Acetylene is a linear molecule, and when we look at it, it looks the same left and right, okay? So it has 2 identical groups on either side. Great. Number 5 is a trigonal planar molecule that does not have 3 identical groups. Awesome. You guys are doing so great determining the overall polarity. And lastly, number 6 is very similar to the cases of 1 and 2. Great job. That is polar. So as I said in the instructions, when it comes to this, in order to make a solution, the polarity of the solvent needs to match the polarity of your molecule. So what this means is that in order for CH3, oh, I actually changed the chemical formula. Let me change this. I gave you guys a different compound. I put 3 Cls instead of only 1. Let me just do this again. It's still the same answer. It's still a polar molecule. There you go. That looks better. So for number 1, that is a polar molecule. So if I want to make a solution with it, then I need a polar solvent to make that solution. For number 2, for dihydrogen monosulfide, if I want to make a solution, since the molecule is polar, I need a polar solvent to make a solution. For number 3, that is a non-polar compound. So if I want to make a solution with it, I need a non-polar solvent. Number 5, since it's a polar molecule, I need a polar solvent to make a solution. And number 6, since it's a polar molecule, I need a polar solvent to make a solution. Okay? Put a 1 in the chat if you want to at least try 9 through 12. Awesome. So at this time, I'm going to give you guys two minutes to do this. I'm going to do for you the Lewis structures for the 2 covalent compounds, which is 10 and 11. So this is the Lewis dot of ammonia. And that's the Lewis structure for hydrogen monobromide. Okay, so I'll give you guys 2 minutes to determine what type of solvent do we need in order to make solutions with those molecules. Okay, let's go over the answers. First, we have magnesium phosphate. So remember that magnesium phosphate is an ionic compound, so we need to apply solubility rules. So is magnesium phosphate soluble or insoluble in water? Magnesium phosphate, can we dissolve it in water? Yes or no? It's insoluble. So since we cannot dissolve it in water, then we need a non-polar solvent in order to make a solution with it. There we have the Lewis dot structure for ammonia. Okay. Ammonia, since it's a covalent compound, we need to draw its Lewis structure and determine the polarity of it. So is ammonia polar or non-polar? It's a tetrahedral molecule that does not have four groups that are identical. Exactly, that is polar. So it needs a polar solvent to make a solution. Hydrogen monobromide, that is a linear molecule that does not look the same. It doesn't have two identical bonds on left and right. So is it polar or non-polar? Excellent. So this is a polar molecule. So it needs a polar solvent. Okay. What about silver hydroxide? Is it soluble in water? Yes or no? Silver hydroxide is not soluble in water. So that's why it needs a non-polar solvent in order to make a solution. Questions about if you're given a compound and you need to determine the solvent that is required in order for it to make a solution. Now we are going to move on to section 9.2, where we're going to learn about electrolytes, okay? So electrolytes, understand that these are going to be compounds, okay, that are going to either form or not form ions in solution. That's what makes them an electrolyte or not an electrolyte. In addition, if you pass a current through it, it can conduct electricity, depending on the type of electrolyte that it is, because there are some electrolytes that are not able to do that, okay? Now, understand that electrolytes are very important, okay? Because electrolytes play important roles in maintaining proper function of cells and organs, okay? As you can see, they balance the fluids in your body. They maintain your body's proper pH, which we're going to learn in chapter 10 tomorrow, that pH is going to make sure that we have the correct balance of, or I should define pH as the concentration of hydrogen ion, okay, in a particular solution. And because many of the biomolecules that we have in the body work at a particular pH, we have to watch the pH, okay? And lastly, electrolytes also carry electrical signals to power the nerves and even muscles, okay? If by any reason you have been drinking or eating electrolytes, as you can see, some of the electrolytes are present in food groups, okay? So you can actually have a drink that is full of electrolytes. So as you can see, Pedialyte has sodium ion, potassium ion, chloride ion. Or for example, if you decide to go for a particular fruit, like banana has a lot of potassium. Or if you decide to drink your electrolyte, if you have coconut water has sugar, but it also has electrolytes in it. So it depends on how you consume it, but understand that electrolytes are very important for the body. okay? Now, let's define the different types of electrolytes. We can have a strong electrolyte, we can have a weak electrolyte, or we can have a non-electrolyte, okay? So as I said, by definition, strong, weak, and non-electrolytes is going to depend on what they form once you put them in solution, and usually the solvent that we're talking about is water, okay? So if we focus on the left side of our slide, as you can see, a strong electrolyte completely disassociated into ions in an aqueous solution. So this is going to be ionic compounds that are soluble in water, okay? That's one of the examples. In chapter 10, we're going to see that there are some covalent compounds that make ions when you put them in water. For now, because we are dealing with this, understand that for now, based on our discussions and the knowledge that we have, ionic compounds that are soluble in water are going to be your strong electrolytes. Let me just make the note here. In chapter 10, we will learn about covalent compounds. That form ions in water. So again, when it comes to these ionic compounds that are soluble in water, they're going to separate in the cations and anions. If you put an electrode in the solution and then you try to pass a current through it, and the light bulb is going to indicate if the current is able to go through, what we see is that in that electron, we have a positive end and a negative end. The cation will go towards the negative end of the electrode. The negative anion will go towards the positive end of the electrode. So, so what this means is that if you pass the current, since all you have in your solution are ions, this is able to carry the electrical current, and that's why we see a bright light bulb, okay? Let's go through the second class, which is a weak electrolyte. When it comes to a weak electrolyte, this is going to be a compound that when you put it in water, it's going to just stay as a molecule and it forms very few ions, okay? As you can see here as an example, HF, out of all the different acids that are formed with group 7A in the periodic table, is the only one that actually, when we put it in water, it stays as molecules, and there's only a few ions that form. So because mostly this compound stays together as a molecule and only a few ions are formed, then those few ions go through different ends of the electrons, okay? And if we pass a current through this solution, we only see a dim light, because in our solutions, we have very few ions. Then we have a non-electrolyte. In a non-electrolyte, you can dissolve it in water, okay? But it stays as only molecules. There's formation of no ions in it. Sucrose is another term that is utilized for table sugar. And we know that table sugar dissolves in water. And if you didn't know, now you know. So the reason why sucrose is able to dissolve in water is because it has a lot of carbon OH bonds. So these squiggly lines here are just representing that carbon atom that is bonded to OH is bonded to other things. So the main reason why sucrose can dissolve in water is because it has this type of bonding. Carbon is bonded to OHs, okay? So because of that, we can dissolve it in water, no problem, but it remains as a molecule. Since there is no ions that are attracted to the electrodes, then understand that overall, when we try to do that experiment of looking at does this solution pass an electric current, you can see that a non-electrolyte is not going to pass that electrical current through it, and we see no light bulb be turned on. Okay. Now, when it comes to these concepts, you guys need to know the definitions of the different electrolytes. So at this time, I have a list of terms that we have talked about so far in this chapter. So I'm going to give you guys 3 minutes to read through the terms that we have on the left column and pair them with the correct letter on the right column to define the term. So I'll give you 3 minutes to pair these terms and their definitions. Let's utilize the letters to pair these terms. What letter corresponds to the definition of solution? Great. Number 2, the definition of solute. Definition of solvent. You guys are doing so awesome. Definition of soluble. And let me warn you something, because I don't know how this happened, because sometimes I put it in the instructions and I'm still amazed at why is it that the reading doesn't translate to the answer. When I ask you a question in the exam and you have to type soluble, soluble is spelled S-O-L-U-B-L-E. I don't know why. Let me warn you now. I hope you guys that are here in class and people that are in the rewatch or rebroadcast of this, please don't make this mistake. I don't know how people spell soluble like this. It's not how you spell soluble. The correct spelling of soluble is on number 4. I look at this word and in my brain, again, English is my second language, but that says soluble, not soluble. So understand that if you need to type the word and I give you the word, please type it correctly. So the word on the top, S-O-L-U-A-B-L-E, is not correct. That's not how you spell soluble or insoluble for that matter. So let's just understand that chemistry also is kind of like a language. So let's spell it correctly. Number 5, alloy. Great. Number 6, aqueous solution. Excellent job, you guys. And lastly, electrolyte. Great. Now, in letter D, it says substance that dissolves in water to form a solution that conducts an electric current. Okay? Now, if I ask you what type of electrolyte would that be? Which one will be the one that this one corresponds to? Excellent, strong. A weak electrolyte can also conduct an electric current, but understand that when I define it, we need to add to this in order for it to be a strong electrolyte. Forms ions in a solution. So I just want to specify that. Strong electrolytes and weak electrolytes can conduct electricity. Strong is doing it better. So the key of defining, okay, so if it conducts electricity, how do I distinguish between strong electrolyte and weak electrolyte? The formation of ions. If it's just ions and no molecules, then it's a strong electrolyte. If there's molecules and a few ions, then we're dealing with a weak electrolyte. Okay? Any questions about the definitions? So let's move on to section 9.3, where we're going to be dealing with solubility. Solubility is defined as the maximum amount of solute that dissolves in a particular or a specific amount of solvent. Understand that solubility is actually temperature sensitive depending on the solute. And whenever we're dealing with solubility, it can be expressed as grams of solute in 100 grams of solvent. And the solvent that we mostly use is water. Here we have another illustration in which we're making a saltwater solution. And you can see in the image that we have in the bottom right corner of the slide, the interaction between the water molecules and the ions in the ionic compound, okay? Now, when we are trying to make solutions, there's different classes of solutions, okay? Solutions can be unsaturated and they can be saturated solutions. An unsaturated solution contains less than the maximum amount of solute, so that the amount of solvent that you have can hold. So you can always dissolve more solute in an unsaturated solution, okay? A saturated solution, on the other hand, contains the maximum amount of solute that can dissolve in a given solvent. And at times, when we have a saturated solution, we see that there are some of the solute in the bottom of the container, okay? Now, we also have another type of solution, which is called a supersaturated solution. A supersaturated solution contains more than the maximum amount of solute that can dissolve. Temperature is used to accomplish this, okay? So we can create supersaturated solutions. Let me go to YouTube and show you guys an example of a supersaturated solution. Sodium acetate, crystallization. So I'm going to show you guys a video. Give me a few moments.
Welcome back. Now, as promised, the dancing scientist from UCLA, aka Jeffrey Vinegar, is here to dazzle us right now in the Daily Planet. Welcome back. Now, as promised, the dancing scientist from UCLA, aka Jeffrey Vinegar, is here to dazzle us right now in the Daily Planet studio with his scientific wizardry. And get ready for this, because you're about to see some liquids that
Can you guys hear it? Yes or no? So please let me know, you guys, because I need to make sure that you guys hear it. Okay.
you should not drink.
Okay, I'm sure you've tried to make forts out of snow, you've made them out of pillows, but have you ever made them out of liquid? Well, today we are here with Jeffrey Vinegar. He's the dancing scientist from UCLA. And Jeffrey, you've got some iced tea here. What's going on?
I do. So have you ever made lemonade, for example, and had a lemonade stand?
Yes, I have, with my entrepreneurial spirit.
Nice. So when you make lemonade or iced tea, you kind of put sugar and water, and you mix it up, and it dissolves, and you can keep adding more and more. But there kind of comes that point where you just can't get any more to dissolve.
Yes, because it tastes gross.
I think it tastes the best in that case. But basically, scientists call that a saturated liquid. It's holding as much solid as it possibly can. So this would taste good if we added a lot in here, but I got something cooler.
Okay.
This liquid is really sensitive, and it's a super saturated liquid. That means it's holding more solid than it should be right now. You can kind of think of a person carrying a lot of boxes, a really big tower, and they're kind of handling it, but if you add one more box, or if they knock into something, it all falls down, kind of
Gotcha.
crashes.
Okay.
So that's exactly what can happen here. I just have these crystals, and if I were to add...
What are these crystals first?
This is a salt called sodium acetate.
Okay.
And you can actually make it from baking soda
Sodium
and vinegar.
acetate, and what's in here?
That's just water and sodium acetate that I dissolved earlier. And so if I just take like one little crystal and drop it in there,
Okay.
check
It's
out
crystallizing
what's
very
happening.
quickly. Oh my goodness, it almost looks like an iceberg is forming in
It's
there.
spreading out, and it'll soon fill the entire thing. Why don't you hold that and feel it and tell me what you feel?
Well, it seems to be warming up a little bit,
It is.
huh?
This is actually one of the methods they use to make hand warmers, the kind that
Okay.
you can warm up and reuse. So that
So this is
liquid-
just all the energy coming out as heat right now.
Right, crystallization releases heat. It's exothermic, as scientists call it.
You can see the steam in there, you guys, huh? Okay, wow, so this is a solid
Yeah,
now, just
you
like
can
that.
actually move it around, and it's solid.
Wow.
That was a super saturated liquid.
Okay,
and-
but I want to get to the making forts.
Totally. All right. I have a lot more here, as you can see. And
Okay.
so if we take these crystals and sprinkle them on the table,
Okay.
like this, we can make forts or castles using the liquid. So why don't you grab one right over there, throw on our safety
goggles, safety first, safety first.
And by pouring the super saturated liquid on the seed crystals, we can try to make towers. I'll try to demonstrate for you here.
Oh, look at that. That's wonderful.
Go ahead, give yours a try.
Okay, I'm
You
gonna.
got to pour it slowly, and we can build a tower. And don't forget, we're trying to make a fort or a castle.
Okay, I'm gonna do the. Oh no! Look, I jimmy jammed it. I touched it.
Go ahead and grab another one.
So is this similar to how a stalagmite forms in a way?
In a sense, but this is actually more similar to the way rain forms. Rain, where water vapor in the sky, it needs something to start forming a droplet.
Okay.
And that's usually dust that's in the sky, and also little clay particles that are naturally in the air.
So in this instance, then, what is it that triggers the crystallization?
It's a little seed crystal, which kind of provides the surface and the structure for all the other crystals to start forming around. It's kind of a repeating pattern. That's what a crystal is kind of defined as. And so it provides that initial structure that all the other crystals form on.
You'll have to forgive me. I'm clearly not very proficient at fort building in
this seems
in
not to
liquid
be
form just yet.
A
but
fort. What do you think this looks like? I don't know.
I'm not too sure exactly. I'm just trying to create some sort of level or some
I'm gonna
sort
try to
of barrier
build
as it
this
is.
as high as I can, so we can protect the fort.
Okay, I'm going to build on top of yours to see how
Okay, go
high we
ahead.
can make it.
I'll move over here
That's
and
fine.
try to fill in this area.
This is so much fun. So why isn't this damaging the surface of the table here?
Well, basically, it's just got water and sodium acetate. Sodium acetate is a safe chemical. You can actually make this at home if you wanted to with parental supervision. By mixing baking soda and vinegar, you can make this salt.
Okay.
But the challenge is it has to be really pure, because if it's not pure, or you get a little piece of dust in it, this happens.
That's exactly
So it
what
crystallizes.
happens.
Look how tall that is.
That is
It might fall over. Oh.
fantastic. Thank you so very much,
Not quite a
Jeffrey
castle, but still pretty
Vinegar. Hey, I'm going to work on it. I'm going to
Sounds
get
good.
better, I promise. Thanks so much.
Of course.
So as you guys saw in the video, when we have a super saturated solution, they are not really stable. So when you saw that the percenter actually moved it a little bit too much, then all of a sudden crystallization or nucleation started happening. That is also the process that happened when they were like pouring the sodium acetate solution onto the desk, because the crystals were already there. Then that was what was allowing all the crystals to be forming. And indeed, this reaction is exothermic. So when the crystals are forming, energy is released. And as we saw in the video, this is one of the ways that when you need or you buy hand warmers that you press on it and all of a sudden it feels warm and you can reuse, is because you are crystallizing sodium acetate. And then when you try to revert it, then understand is like you're trying to solubilize it again. So be inspired by all the science that we're learning here. And one of the things that you guys saw at the beginning of the video was the whole idea of like in a lemonade stand, when you are trying to make your lemonade, you can add, okay, just sugar to it, right? But for example, for those of you that enjoyed this drink or have tried it, or you know people that make it, or you know people that have tried it, when you're making sweet tea, which we can have it commercially available at Cane's, Yum. When people are trying to make sweet tea, the reason why I brought up the idea of temperature is because we know that sugar in water, its solubility increases as we increase the temperature, okay? So for those of you that know how to make sweet tea, you understand that you have to warm up your water, then try to solubilize as much sugar as you can, then you leave it at room temperature, and that's how you get all the sugar that you can. That's kind of like if sweet tea, it depends on where you buy it from. Sweet tea can also look very like syrupy, because the viscosity of the solution will be so high because it has so much sugar. That's why the consistency of the sweet tea can have. Also, if you're at home and you're trying to solubilize things, for example, you're trying to add sugar to your tea or coffee, it makes a difference if the liquid is hot or not. So to accomplish a supersaturated solution, understand that depending on the conditions in which your solute is going to have greater solubility in the amount of solvent, then we need to increase in temperature for many solids, because that's the trend, or decrease the temperature if you're trying to solubilize gases. But understand that temperature is specifically what is utilized in order to make supersaturated solutions. So there's a question in the chat. Is the video similar to how you make candy crystals? No, it is. You're correct. So when you're trying to make rock candy, it is a similar concept. You make a supersaturated solution, and then the goal is that if you put a crystal on where you're trying the candy to harden, then rock candy will go into the stick and it will basically crash out of the solution. So if you're making rock candy, that is one of the techniques that is utilized, making a supersaturated solution. So as I was mentioning, when it comes to having a solution, two things affect the ability of things to be soluble. The first one is temperature, as I just mentioned. And when it comes to solubility, again, if we have solids, most solids, as you increase the temperature, it increases its solubility. And you can see specifically in this graph how for a lot of solids, potassium iodide, glucose, sodium nitrate, potassium nitrate, for sodium phosphate, not so much for sodium chloride, which is interesting. But for the majority of them, as you increase the temperature, the solubility of them increases. Now, understand that for gases, that is different. For gases, solubility decreases as the temperature increases. Okay? Now, I don't know whoever had to experience this, hopefully none of you guys, but in a way, for those of you that have such practices, please don't do this at home. If you leave a soda in your car, okay, remember, soda has carbonation. There's a gas that was put into the container. And let's say that is a beautiful summer day and it gets really hot outside. The gas that is in the liquid is not going to be as soluble in the liquid because when temperature increases, that gas can no longer be contained in the liquid, okay? So understand that if the pressure that is built in there is enough because there's enough gas, that's why, unfortunately, I've only seen it once in the parking lot of Vallarta supermarket in Escondido, where there was soda that started exploding. Like, just imagine the big jugs, like the 2 liters, just exploding inside of a car because it was really hot. And the person was just like, oh, it's fine. Nothing was going to happen. Inside of the car, it can get really hot. And if that gas that is in the liquid, it becomes insoluble and it increases the pressure, it's going to pop. Okay. So understand that not all solids have the same trend with temperature. And in terms of solids, as temperature increases, they become more soluble. But in terms of gases, as temperature increases, their solubility decreases. The other thing that can also affect the solubility of gases specifically is going to be pressure. Pressure is going to be specifically defined as the force against the container. So that's the force that your molecules are going to exert on the container. So understand that when that pressure, okay, is increased, then the solubility of the gas is going to increase in a liquid. All of that is given by Henry's law. And as you can see here, Henry's law specifically states that the solubility of a gas in a liquid is directly related to the pressure of that gas above the liquids. So if we increase the pressure, then more gas molecules are able to dissolve in the liquids. Okay, so let me see, there's some questions. Oh, wait, somebody had an unfortunate. See, somebody had that happen. Now you know, it's all, you know, chemistry. There's some comments in the chat. This explains what soda can be swelling left in the freezer. No, when sodas are swelling in the freezer, that is because that liquid, the property when it freezes is expanding. So that's why they explode. It's not the gas trying to escape. Now, what is really true, which growing up at home, like my mom will always get annoyed when we left. Like, let's say that with dinner, for some reason, she gave us soda. If we take the refrigerated soda and left it on the counter, my mom will not be happy. Be like, you guys, what are you doing? You leave it on the counter, it's gonna become flat faster. But now as a chemist, I'm like, you know what? My mom always knows best. Because indeed, When you have a soda that is refrigerated and then you leave it on the counter and it becomes room temperature, the minute that you open it and you hear the sound because the gas is released, remember that there's more gas molecules that are being released as it's getting warmer because it's at room temperature. So indeed, just like she was telling us, it will become flat faster. So yeah, those soda explosions are interesting. Thank you for the little stories in the chat. I appreciate it, and everybody can learn something from it. So this concludes today's lecture. Tomorrow we will be doing some math problems related to chapter 9. We will be looking at concentration and we will be looking at dilutions.